Hello everyone, this is Suhail Mansoor from Optimized Solutions LLC, and I'm very excited to introduce a software product that is developed and marketed by my company as a toolkit to design and optimize engine mounting systems. The name of this software program is a Raptor, R-A-P-T-O-R, which is an acronym for Recursive Algorithm for Parametric Tracking of Resonance. In this short video, I'll be demonstrating the basics of Raptor by using a simple example problem. First, a bit about Raptor. This is a Windows-based program that can be operated from a basic laptop computer. It can be purchased from Optimized Solutions directly. If there is interest to procure Raptor, please feel free to email me at the following address, mansoor@opsollc.com. You may also want to visit the company website at the following URL, www.opsollc.com. Perfect. Let me now introduce the example problem. Let's assume that the engine is supported by a system of 3 mounts. So we have an engine which is supported by 3 mount system, and these mounts are fixed in location with respect to the center of gravity of the engine. The mass of the engine is 500 kilograms. The center of gravity is located at x is equal to negative 800, y is equal to 800, and z is equal to 400 millimeters in the vehicle coordinate system. The mass moment of inertia tensor is defined by the main diagonal terms of Ixx, Iyy, and Izz at 32, 26, and 28 kilogram meter squared respectively, while the Ixy, Ixz, and the Iyz terms are all 0.5 kilograms meter squared. So this information that you see here is generally provided by the applied mechanics group or applied mechanics team of the vehicle or the engine manufacturing. The forcing function on the engine is defined as a force of 400 newtons and a moment of 700 newton meter that could be due to a belt load, say, and a torque due to an engine event such as max throttle, what have you. The mount locations are defined then right here, and basically what you have is our coordinate locations in the vehicle coordinate system or the global coordinate system, where mount X is at negative 400, 400, and 300. Mount 2 is at negative 400, 1200 and 200, and mount 3 is at negative 1200, 800, and 600. So it gives you an idea what the mount locations are. The mount stiffnesses here are unknown. We do not know what the mount stiffnesses are. And what we are trying to do, what our objective function here is that the vehicle NVH engineers have determined a modal optimization matrix that this vibratory system must comply with. The goal of this matrix is to decouple vibration, meaning that each of the 6 degrees of freedom that has to have a vibratory mode shape that is to be within a tight tolerance and with a certain amount of purity. So, for example, the first mode shape should be in the z direction, and we should be between 8 plus minus 2 hertz with a purity of 85%. Similarly, the third mode shape should be in the x direction between 12 plus minus 2 hertz with a purity of more than 85%, and so on and so forth. So this is our objective function. This is what we are trying to optimize for, and the values that we are trying to optimize are the mount stiffnesses, as I explained. The objective is to determine the 3-dimensional stiffnesses then for each of the 3 engine mounts that satisfy this modal optimization matrix. So what we have here is a sample of a very traditional engine mounting problem that needs optimization that needs to be solved. So in order to actually solve this problem, we will be opening up the Raptor software program, which I will do next. And on opening the Raptor software program, you can see that there are several things that are happening here. And what I will do is I will open up the example file that I had saved earlier. And this is my test file. And what you will see here is the boxes are now populated with the actual values that I had saved. So it may be a good time at this point to actually go through and try to understand what is going on here and where the information that we have is actually fed into the software. So the Raptor main screen consists of several portions. The top portion is a file menu, which has it's a navigation bar which helps you go through the different parts of the software. The left-hand top area here is an optional project information entry port where we can put in information about the system of units used, the engineer, the company, what have you. Right below, we have got the mass properties. So in this case, it's the engine. So the mass of the engine, the location of the center of gravity, the inertia tensor, as I had explained, the forcing function. And then below that, in the bottom left-hand portion of the screen, we have got the modal optimization matrix. This was the same thing as the problem statement. The first mode is a Z mode with a frequency of 8 plus minus 2 hertz with a dominance of 85% or greater. Second mode is a Y mode, a frequency of 10 plus minus 2 hertz, modal dominance of 85% or higher, what have you. And this is where we feed that information in. We need to optimize the system for 6 modes. So all 6 modes need to be satisfied. In the center portion of the screen here are the actual spring properties. So the first thing that we need to enter is how many springs do we have. In this case, there are 3. And then we enter the location of each of these springs in the vehicular coordinate system or the global coordinate system. Then we enter the stiffness values for each of these springs. So you can see there is the Kx, Ky, Kz for the first spring, and Kx, Ky, Kz for the second spring, and the third spring, so on and so forth. So what we have here are just dummy, or what I call seed values of 1,000 each, because really we don't know what this stiffness is. So we just enter some seed values and we create a system. The value for increment here determines how fine or granular must the solver be, and the value for tolerance here determines how broad or what the spectrum of stiffness should the solver actually solve to. So the breadth of the solver is determined by the tolerance. The increment determines more the amplitude of the solver. However, you can see that this is a very similar way as we had designed the problem. We set the problem up in Raptor. Now, the first thing that we do is in Raptor, we have under solver, we have got in calculate and then several different optimization algorithms. First thing that we do is do a calculate, and the calculate just takes a snapshot of this system and shows where we are. And if I just do a snapshot, basically not an optimization, but it's just taking the stiffness that will be fixed at 1,000 each, this is the type of modal response I get. And what I see here is the first mode is a Z mode, but it is at 11.48 hertz. Second mode is a Y mode at 11.81. Third mode is, so on. And you can see the sixth mode here is an RZZ at 28.6 hertz. And you can see these don't satisfy this modal optimization matrix. And that is pretty obvious. We have just dumped in some general seed values, and we don't expect these to satisfy the modal optimization matrix exactly. However, this is exactly what Raptor does. Is if we go now to the solver and we hit this button called auto optimize, then basically what happens is Raptor goes and it is trying to seek out the modes. As you can see, these boxes are turning from gray to white, and as the software is going and finding the modes for us. And simultaneously, you can see the Kx, Ky, Kz numbers are also being changed as the software is narrowing down to a solution. You can see the fourth mode is found. Now the software is working on the fifth mode. And basically, it is seeking out and trying to see if it can optimize to get a value for the fifth mode. Now, this would take an enormous amount of time, matter of perhaps days or even weeks to do by hand, because each of the iterations is going to be having to change each of the stiffness values and basically run the calculation again, so on and so forth. And there we go. Finally, we have got a solution here generated by Raptor that totally satisfies the modal optimization matrix, meaning the first mode is between 8 plus minus 2 hertz, this is 7.71 hertz. Second mode is between 10 plus minus 2 hertz, a Y mode, and you can see that is 8.37, so on and so forth. And last mode you can see is the RZZ is 20 plus minus 2, and you can see, and each one of the modes has a modal dominance of at least 85%. So there we go. We have just solved the problem in a relatively small amount of time. And if you go to the status window, you can see in solving the problem, the program went through 44,017 attempts, and it required only 55 seconds or so to solve the problem. And what we have here is a fully optimized system which yields the appropriate result that satisfies the modal optimization matrix. So very quickly, as you can see, we can generate an optimized solution. And if we go to the file utilities and save a report file, and I'll just override the one I had done earlier. And what you will see here is under applications, you can open this report up in Notepad. And what you will see here is as we go down, you can see all the information that is generated in this report. All the input information, the spring information, all the coordinate transformations from the vehicle coordinate system to the global coordinate system to the engine coordinate system, so on and so forth. The displacement and force calculation, each of the mounts, the main mass displacement in each direction, in angular and translational, and finally frequency calculations, which are the normalized eigenvector and also the relative kinetic energy in the mode, so on and so forth. And then it gives you some idea about what happened during the solution and what have you. So this report can then be either cut and paste into your favorite word processing program and or an email program and sent to the customer, sent to internally sent within the organization, what have you. So now these numbers that the software generates for the X, Y, and Z can be rounded off, and a very clean file can now be generated. Open that up. And you can see I've just rounded these stiffness numbers. And now if I hit a calculate, I should get a perfectly optimized system with nice round numbers for every stiffness. And these round numbers now can be then generated into the appropriate engine mounts. And or if you have a database, you can do a search and actually obtain the correct database entries for each of these numbers. So, this is a general example of optimization. There are several other types of optimizations that can be done here, several other parts of the software, which we don't have time to discuss in this tutorial, but I'll be making several other tutorials that will deal about those portions of the program. Hopefully, this demonstration has been helpful to you to understand the basic operation of Raptor software program. Thank you very much.